Hello everyone, I am Osamu Kada. In the previous two videos, we proved the Cayley Hamilton Theorem from the approach using the notion of matrices whose components are polynomials in the matrix in the first video, and from the approach using the notion of R module. Here, ring R is a polynomial ring Rt. Today, I'm going to prove the theorem from the approach using the notion of polynomials rings whose coefficients are matrices. It states as follows. Cayley Hamilton Theorem. Let A be a n times n matrix whose components are real numbers. Instead of real numbers, we may take any commutative ring R. Let P of T be the determinant of Ti minus A, the characteristic polynomial of A. Here I is the identity matrix, and P of T is the element of polynomial ring Rt. Then we have P of A is equal to the zero matrix. Now we give a proof. First, we give two elementary lemmas concerning matrices whose components are elements of polynomial ring Rt. We give proofs for completeness. For any Ct in MnRT, n times n matrix whose components are polynomials, there exists a natural number m, and there exists Cp, which is the element of MnR, n times n matrix whose components are real numbers, for p equals 0 to m, such that C of t is equal to summation from p equals 0 to m of the t to gp times Cp. Let Cij be the ij components of Ct, and Cij is equal to Cij summation from p equals 0 to m of the Cij times t to the p. Then C of t is this polynomial is the ij components, and putting at t to gp, we have C of t is equal to summation from p equals 0 to m of the t to the p timesCijp. And denoting this matrix Cp, we have C of t is equal to summation of t to the p times Cp. For instance, this matrix is equal to t squared times 1, 1, 1, and t times minus 1 and 2, and 2 times 0, 1, 0. Next lemma is that two matrices C of t and D of t whose components are polynomials, denoting like this. If C of t is equal to D of t, then for all matrices A whose components are real numbers, substituting A for t, we have denoting this element as C of AL. This L means that substituting from the left, C of AL and D of AL are the same. And similarly, C of AR is equal to D of AR. C of t is equal to D of t means that all ij components are the same, and ij components are the same means that all coefficients of t to the p are the same. SoCijp is equal to Dijp for all ijp. Since ij components of Cp is equal toCijp, so this means that Cp is equal to dp. Cp is equal to dp means that multiplying a to the p from the left and summing up, we have that this is equal to this, which means that C of AL is equal to D of AL. L means that substituting A for t in D of t from the left. And similarly, for C of AR is equal to D of AR. Now back to the proof of the Cayley Hamilton Theorem. Let B of t be the Ti minus A. This is the n times n matrix whose components are polynomials in T. Let B of t tilde be the adjugate matrix of B of t. Then we have B of t times D of t tilde is equal to B of t tilde times D of t, which is equal to determinant B of t times I, and determinant B of t is equal to Pa of t. This is equal to the characteristic polynomial of A times I. So denoting B of t tilde summation from p equals 0 to n minus 1 of the t to the p times Bp. Here Bp is an n times n matrix whose components are real numbers. We have B of t times B of t tilde is equal to ti minus a times summation of t to the p times bp equal to the summation of ti times t to the p times bp minus summation of a times t to the p times bp, and this is equal to the t to the p plus 1 times bp, and this is equal to t to the p times a times bp. Let characteristic polynomial p of t be equal to the summation from p equals 0 to m of the ap times t to the p. Then determinant b of t times I is equal to summation of ap times t to the p times I, and this is equal to the summation of t to the p times api. So denoting b times b tilde of t by b of t times b of t tilde, by the above lemma we have b times b tilde of a left is equal to b times b tilde of GAL is equal to determinant b of dot times I of GAL and a to the p plus 1, and this is equal to a to the p plus 1. So this is equal to 0 matrix. So we have PA of A is equal to 0 matrix. We can give the proof in another way. There is a ring isomorphism from the n times n matrix whose components are polynomials, and the polynomials whose coefficients are MNR, the matrices, by defining C of t denoting the summation of t to the p times Cp to the summation of Cp t to the p. Phi of this matrix coefficient of t squared is 1, 1, 1, and the coefficient of t is equal to minus 1, 2, and the coefficient of 1, 2. By this isomorphism, we identify the matrices whose components are polynomials as polynomials whose coefficients are matrices. Let C of t be the summation of Cp times t to the p, which is a polynomial whose coefficients are matrices. Define C of a right to be the summation of Cp times a to the p, and define C of a left to be the summation of a to the p times Cp. We have the following lemma. Let C of t and d of t be the polynomials whose coefficients are matrices, and assume coefficients of d of t commute with a, that is, denoting C of t is the summation of dp times d to the p, coefficients of d of t is dp, and adp is equal to dpa. Then C times d of a to the right is equal to the C of a right times d of a right. Similarly, if coefficients of C of t commute with a, then C times d of a is equal to the C of a left times d of a left. The proof. C times d of t is equal to the summation of Cp t to the p times summation of dq t to the q, and this is equal to summation of Cp times dq times t to the m, here m is equal to p plus q, and C times d of a right is equal to summation of Cp times dq times a to the m. A to the m is equal to a to the p times a to the q, and since adp is equal to dpa, we have dqa to the p is equal to dqa times a to the p minus 1, and dqa is equal to adq, and so on to equals to a to the p times dq. So dqa to the p is equal to a to the p times dq. So this is equal to the C of a right times d of a right. Since the coefficients of b of t, I and a, which commute with a, we have b tilde times b of a right is equal to b tilde of a right times d of a right. And b of a right is equal to I times a minus a, which is equal to 0 matrix. So we have b tilde times b of a right is equal to 0. And since p tilde times b is equal to p of a times I, and this is equal to 0 matrix, pa times I of a of right is equal to summation of ap times I times a to the p. Since pa of t times I is equal to the summation of ap times t to the p times I, which is equal to ap times I times t to the p. So pa times a of the a right is equal to summation of api times a to the p, and this is equal to summation of ap times a to the p, which is equal to p of a. So this implies that p of a is equal to the 0 matrix. Let us consider the following example. Let A be this matrix. Then b of t equals to ti minus a equals to this matrix. And the characteristic polynomial of a is equal to determinant b of t is equal to t cubed plus 2 times t. And the adjugate matrix of b of t tilde is equal to this matrix. And this is equal to t squared times I plus t times this matrix plus this matrix. Denoting this matrix b1 and denoting this matrix b0. b of t is equal to t squared times I plus t times b1 plus b0. Then b of t times b of t tilde equals to p of t times I, which is equal to t cubed times I plus t times 2 times I. And b of t times b of t tilde is equal to ti minus a times t squared times I plus t bi plus b0. And this is equal to t cubed times I plus t squared times b1 plus t b0 minus t squared times a plus t times ab1 plus ab0. So substituting a for t from the left, we have a cubed minus a squared times a, this is equal to 0, and a squared times b1 minus a times b1, which is equal to 0, and ab0 minus ab0, which is equal to 0. So this is equal to 0 matrix. P of a is equal to a cubed plus a times 2 times I is equal to 0 matrix.